Let us see how to create specific sets of randomly generated numbers for testing in machine learning. To access random number generators from NumPy, you go to the numpy.random library and you import the random number generator that you need. So let's use uniform. In addition to the random number generator, we need to have the seed function. So we can use this to generate uniformly distributed random numbers. So a uniform distribution always needs to have a lower and an upper boundary defined. So let's do that. Let's define a lower boundary as 0 and the higher boundary, the upper boundary, as 10. So we'll get numbers that are somewhere in the interval between 0 and 10. And then a convention in machine learning is to call the rows samples and to refer to the columns as features. So let's learn this. Samples features equal, I use 1 and 2, so that will give me one sample with 2 features, or in conventional speaking, 1 row, 2 columns in a NumPy array. So now that we have defined it, we now need to know how to initialize the random number generator, and that's called seeding. So we pick a random seed, which is actually not random but a specified number. So we can use an integer to initialize the random number generator such that it starts from a specific starting point. So in this case, the starting point would be 1, 2, 3. And then we make that happen by calling the function seed on that number. So that will now have the uniform seeded, and we can create the variable called random numbers. We can create our random number array called random numbers, calling the uniform random number generator. We need to specify the upper and lower boundary. Low equal low and high equal high specifies it. You can see in this case there's no problem with using the same name for the variables that define the boundaries and the keyword arguments. Keyword arguments are not affected by any variable definition in your script. So finally, in addition to upper and lower boundary, we need to specify how many samples do you want, or how many numbers do you want. And that is the keyword argument size. Put that into a tuple because we have 2, and the first is samples and the second are the features. So this is a very generic way of doing it, and we can have a look at the outcome. In this case, when I execute the code, 2 numbers, the first one being 1.915 and so on. So to understand this effect of seeding, if I now copy that code without the seeding, so call the random number generator again and create a set of random numbers and display that random numbers, you can see the outcome of this code is different. So now the first number is 4.377. And the reason is because starting from the seed is what we have done in the previous code, and now we have continued where we left off and produced another set of random numbers. So if we wanted to go back to the original, wanted to have the same random numbers, we would copy and paste that code, including the call of the seed function. And you can see, if I scroll down a little bit, now the outcome is the exact same as we had at the very top after calling the seed function the first time. So this is a way to guarantee that however many calls are done in your script to the uniform random number generator, you will make sure that the exact same sequence is generated if you use the seeding procedure and you communicate the random seed that you have set. So this allows you to share code and to have somebody else reproduce the exact same results, even though random processes are involved. Well, now that we have created the random numbers, we can also visualize them. Let us create a couple of more samples. Let's create 100 samples. And maybe instead of looking at all the numbers, just look at the shape of the numbers. Now we get 100,2, which is about what we want to have. And we can plot those if from matplotlib.pyplot we import subplots. And then call it. You know this by now. And then use our plot to make a histogram of the random numbers that we have generated. So I put semicolon there to suppress any other output. If I now put that nice in the middle, then we can see two histograms in one display. And the reason is that the two features each get their own color. So the first feature is the blue histogram and the second feature is the orange histogram. And surprisingly, you can see that they are by no means uniformly distributed. So numbers vary between, say, 4 counts in one case in the orange here, and in the other case it's 17 that were found in that bin. And of course that shows you how careful you have to be with statistical interpretation, but also with interpretation of machine learning results. Having 100 numbers is not a lot. If on the other hand we go back and we create 10,000 numbers, calling that code, so now we go back and execute our plot again, and then you can see the histogram of both features are now approaching at least a uniformly distributed shape, and that shows you that 10,000 is about one of the benchmarks of a requirement for good machine learning success.